Welcome to the Chaos Seminar, the Center for Advanced 2D Materials Homely Atmosphere online seminars. Thank you for being here. Today I have the pleasure to have here Professor Manish Chhowalla from Cambridge University. So Manish is a very distinguished professor. He was in the United States for a long time, and now he's in England. And today he's going to give a very interesting talk about van der Waals contacts on 2D semiconductors. So as you know, in our seminars, Manish will talk for around 40 minutes, 45 minutes, and then you can ask questions. Manish, do you prefer that I read the questions for you, or you want to read yourself?
I can read myself, but if I miss something, then feel free to let me know.
Okay, yeah. All right. So anyway, so thank you so much once again. Folks, enjoy the seminar. Manish, it's all yours.
Thank you, Antonio. Okay, I just need to, do I start sharing the screen or? Right. Great. Thank you very much, Antonio, for that very kind introduction and the invitation for the online seminar. I really like the name of the seminar series because I think it really encapsulates the time that we're in. So I thought before we get into the serious science part of it, I just put up some. Oops, why can't I change the slides? Okay. I know that the coronavirus is a very serious situation around around the world, but we know that we've reached a chaotic point when the virus is afraid of the president of the United States and feels like the virus has to put on a mask. Also, working from home for many of us works quite nicely, but there's some things that we simply cannot achieve by working from home. So I really like this cartoon that I saw this morning. So things have certainly changed for us with the COVID-19 virus overtaking the world, but hopefully we can come back to some new normal and see each other in person, have a few beers and talk science. Okay, let's get to the science part. So I think most of you who are attending the seminar will be familiar with these transition metal dichalcogenides. We wrote this review paper in 2013, just explaining some of the more basic properties, the chemistry and structure and physics of some of these two-dimensional materials. So these are, of course, close cousins of graphene, but they have very interesting properties that are very different from graphene. In one sense, they're true semiconductors, which allows us to fabricate devices in using the traditional sort of methodologies and technologies and physics that we're familiar with. So these are, of course, these MX2 compounds where M is a transition metal, X is a chalcogen. And unlike graphene, a single layer consists of 3 atoms. And if you look at the band structure, even in their multi-layered form, they're reasonably sized band gap semiconductors. This schematic is taken from Goki Eda's group at NUS, where they showed that the weak interaction between the layers gives rise to these states at the gamma point in the valence band. And so the energy minimum in a multi-layered system is between the gamma point and the lambda point, making it an indirect band gap semiconductor when you have more than one layer. But in the monolayer case, the absence of the interactions between the layers transitions the material into a direct band gap semiconductor. And this makes it very interesting for optoelectronic applications. Of course, one can also see that the valence band has a split, and so that gives rise to different states in different valleys, and the splitting is large enough that we can access those valleys as well. But today, in today's talk, I'm going to try to convince you that in fact, just looking at charge-based devices, traditional run-of-the-mill charge-based devices like field effect transistors, are actually extremely interesting when you incorporate these atomically thin body semiconductors, or these 2D semiconductors. So as we know, modern electronics has been undergoing this really aggressive device scaling, and that's led to the high processing speeds that we're all used to. In fact, the clock frequency saturated in around 2003, 2004 at 2 to 3 gigahertz. So the enhanced processing power has actually come from integration of more devices on the same sort of chip footprint. And so what this allows us to do is to have more transistors that do more operations, even though the operations are being done at a saturated frequency of 2 to 3 gigahertz. This sort of revolutionary, one revolution that happened in modern electronics is the realization of these FinFETs. So FinFETs are where the channel actually rises above the planar silicon. And Chenming Hu, who's the father of FinFET, just recently actually received the IEEE medal in 2020. And the real sort of advantage of the FinFET is that because we have the semiconducting channel rise above the plane of the silicon wafer, we're able to place a gate that wraps around the semiconducting channel, and this really improves the gate electrostatics and the power dissipation characteristics of the transistors. But the basic problem when you scale devices down to a few nanometers is this problem of leakage current or off-state current. So this is a plot of the drain current as a function of gate voltage, so the transfer characteristics of a transistor. And one sees that when you apply a gate voltage, we can turn on a device and reach some saturation point. However, the problem is that as you go to smaller and smaller devices, there's an increase in the off-state current. To reduce the overall footprint, the power footprint of this device, we'd like to operate these devices at lower voltages. But that also comes with this consequence of increasing the off-state current. So if we decrease the operating voltage of a device by 60 millivolts, we increase the off-state current by an order of magnitude. And this 60 millivolt per decade is called the subthreshold swing. It's also referred to as Boltzmann tyranny. It's an incompressible limit. So whenever you have devices that are operating based on the principle of overcoming some thermodynamic barrier, we always come up against this 60 millivolt per decade subthreshold swing limit. So if we want to make devices that operate at a much lower voltage, then we have to think of new mechanisms of operation. So I've mentioned sort of power dissipation in electronics. This is not a small problem. If you look at the energy forecast for how power dissipation in electronics and ICT will occur, one can see that the projected energy in electricity demand just from computation, ICT, data centers, that will be of the order of 21% of the total electricity that's produced. And this is because, of course, the transistors, as they become smaller and smaller, they're dissipating a huge amount of power, partly because of leakage current in the off state. So here I've taken a plot where which shows the normalized power dissipation as a function of the year. And of course, over time, the gate length has decreased quite dramatically. The overall dynamic power, the relative normalized dynamic power, has not increased dramatically, but the power in the off state, the static power dissipation, has increased quite dramatically. The dynamic power, of course, is still very high, but relatively speaking, the static power has increased much faster than power dissipation in the dynamic state. And so there's going to be a substantial increase in energy demand from electronics, and it's going to really contribute to a huge amount of energy consumption. And this number is quite interesting. Electronics today, or in the next few years, will account for 3% of the total world CO2 emission. And this is quite interesting because this 3% is the same amount that is contributed from aviation. right? So we don't think about using our laptops as a way of producing carbon. It's very clear that when we take a flight from London to Singapore, there's a large carbon footprint involved. But using your laptop and ICT over a few weeks can result in the same sort of CO2 emission. So that's something to bear in mind. So we'd like to sort of course, decrease this carbon footprint of electronics by decreasing the overall voltage of operation. So how can 2D semiconductors help? Well, if one looks at typical sort of traditional planar transistor, one can work out this characteristic or intrinsic channel length that's dependent on these parameters. And you can see that the other parameters have been optimized reasonably well. The only parameter that's sort of left for further optimization is decreasing the thickness of the channel. And one can do that with 3D semiconductors, but one runs into a problem with introduction of dangling bonds and surface scattering states. So there's a sort of a finite limit that you can thin down silicon or gallium nitride or gallium arsenide. But in any case, if one calculates the characteristic intrinsic channel length with the current sort of state of the art, the scaling for bulk semiconductors is around 10 nanometers. But for atomically thin body semiconductors, naturally occurring atomically thin body semiconductors like single layer MOS2, one can achieve, in principle, devices that are sub 10 nanometer all the way down to around 3 nanometers. And I mentioned electrostatics when I was talking, gate electrostatics when I was talking about the FinFETs. The reason why one needs a FinFET type of device structure is that when one looks at the cross section of a field effect transistor, where you have the gate bias, you have the insulator, and the semiconducting channel, one can see that the influence of the gate bias is the greatest on carriers that are at the interface between the semiconductor and the insulator. But because there is a kind of a probability function distribution away from the interface, some of the carriers that are located away from the interface are able to traverse the source and drain channel, even when there's a gate bias that's being applied. And these less influence carriers that are able to go between the source and drain, despite what the gate potential that's being applied, increase the off-state current that I referred to earlier. When you go from a 3D semiconductor to something that is sub 1 nanometer in thickness, then your probability distribution of the carriers is confined within the 7 angstrom thick semiconductor. And what this means then is that the application of a gate bias influences all the charge carriers uniformly, so the device can be readily turned on and turned off. This allows you to decrease the subthreshold slope close to the theoretical limit of 60 millivolt per decade. So the advantages of these ATBs are that the atomically thin body semiconductors is that they're free of dangling bonds. They can be scaled quite easily down to monolayer. They possess a low dielectric constant, which also allows us to decrease this lambda parameter. And of course, they have excellent gate electrostatics. So in principle, they possess all of the right sort of attributes for us to make devices that are very short channel. An additional sort of parameter that one has to consider when one looks at these very short channel devices with 2D semiconductors is that when you go down to sub 10 nanometers, the operation of the device is more closer to ballistic transport, where there's no scattering in the channel, in contrast to long channel devices. And so if you work out the expression for the drain current in a ballistic transistor, one can see that it's primarily influenced by this parameter TC, and TC is the transmission coefficient, and the transmission coefficient is related to these parameters, primarily this RC. And RC is the contact resistance and due to reflection and backscattering at the source and drain electrodes. So when we go to, although these atomically thin body semiconductors have distinct advantages for short channel devices, the contact resistance then becomes very important, and it's something that has to be addressed. Okay, one sort of, so in addition to short channel devices, one can also look at these tunnel field effect transistors using 2D semiconductors to decrease the energy consumption by reducing the operating voltage. So one of the issues with low voltage operation devices in general is the large is a low signal to noise ratio. That is, when you decrease the voltage, the amount of noise actually increases. So we'd like to realize a device like the tunnel FET that has that is based on the fundamental operating mechanism of a tunnel FET is band-to-band tunneling instead of this overcoming a thermionic barrier. And this band-to-band tunneling gives us very low off-state current. It also gives us subthreshold swings that are less than 60 millivolt per decade. But the main challenge is that the on-state current is lower than for a traditional MOSFET type of device. So one thing that the community is looking at is to realize these tunnel FETs, which gives us this low off-state current, but integrate them with this negative capacitance gate dielectric. So if we put a ferroelectric in series with the gate dielectric, we can achieve this what's called negative capacitance, which provides sort of a boost in voltage or amplification in voltage due to the polarization in the ferroelectric. And that enhances band-to-band tunneling and gives rise to slightly higher current than one would get in a regular TFET. And if we look at these curves, we can see that at a given operating voltage, we can actually reduce the voltage for a tunnel FET while achieving the same current as one would get in a MOSFET. So you know, there's sort of this great deal of interest in tunnel FETs. And in some ways, these 2D semiconductors, atomically thin body semiconductors, are made for realizing tunnel field effect devices. So this is a slide that I took from a review paper by Debti Jenna and Gray Shing from Cornell. And they showed that when one looks at energy versus delay time for electronic devices, we'd ideally like to be in this preferred corner, where you know, and if you look at the devices that are closest to the preferred corner, there are these sort of field effect tunnel FET types of devices. And they did some simulations on devices based on 2D semiconductors that and found that these tunnel FETs with P and N type devices could give subthreshold swings of down to 14 millivolts per decade. This would allow us to operate the device well below the current state of the art. And so they propose this type of device structure, which is simply having a P-type 2D semiconductor and an N-type 2D semiconductor sandwich between two gate electrodes, and this should give rise to device characteristics that look like this. Achieving a good tunnel FET with 2D semiconductors has been difficult. In the previous slide, the schematic that I'd taken was from Ionescu's group at EPFL. They've recently published a paper where they've integrated, I think it's tungsten diselenide with tin disulfide to realize a tunnel FET. So there is some work that's been coming out. But the primary problem has been that it's actually very difficult to have P and N type 2D semiconductors. That is, that in contrast to bulk semiconductors where we can add dopants, we can have a device that runs in accumulation or depletion mode. it's very difficult to dope 2D semiconductors using external dopants, simply because there are just too few atoms in an atomically thin semiconductors to displace one and add another one without disrupting the overall atomic structure. So the approach that one has to take is to engineer the work function of the source and drain electrodes for injecting either electrons or holes into the semiconductor. And that's been a main sort of problem. It's not a very sexy problem, if you will, but the problem of contacts really has become very important in 2D semiconductors, because we've not been able to reliably make both N-type and P-type contacts on different types of 2D semiconductors. So for example, MOS2 is thought to be, it always gives us N-type characteristics, but in principle, there's no reason why MOS2 should be N-type. It should be an intrinsic semiconductor, but the FET characteristics are dictated by Fermi level pinning at the contacts. So let me just summarize the work so far that's been done on contacts. So the main issue with depositing metal on 2D semiconductors is the defects that are created at the interface between the metal and the 2D semiconductors, and potentially defects like vacancies in the semiconductor. And these two effects traditionally lead to Fermi level pinning. And one can do this measurement of Schottky barrier height as a function of metal work function, and plot it for different types of metals with different work functions. Typically, you end up with a slope factor of 0.1, the ideal factor being close to 1. So if you have an ideal, let me go back. If you have an ideal contact that is without any defects at the interface, the slope should be 1. And so to try to overcome this these interface defects, there's been several different strategies that have been tried to depin the Fermi level. For example, side metallic contacts, or placing something like hexagonal boron nitride between the metal and the 2D semiconductor, so that the hexagonal boron nitride acts as a tunnel barrier, and the metal atoms are prevented from causing damage during deposition. A few years ago, we also showed that one can use the metallic phases of the 2D semiconductors to achieve very good contacts. That was followed up by Young-Hee Lee's group, showing similar results. One can also do doping. This is, I think, some work done by Ali Javi's group, where they used local doping similar to what one would do in silicon devices to make good contacts. And as I said, doping of foreign atoms into 2D semiconductors is always a little bit problematic because of high probability of causing damage. Right. So if one looks at some of the experimental work that's been ongoing, it's very clear that as soon as you deposit any sort of metal, palladium, or gold onto a single layer or multi-layer 2D semiconductors, you immediately get these types of defects, diffusion, formation of amorphous layers. And what the real sort of electrical consequences of this is that, in principle, the transfer characteristics should vary with the metal work function. That is, if you use a high work function metal, in the case of MOS2, one should get primarily P-type characteristics. And if you use a low work function metal, one should primarily get N-type characteristics. But you see, from these transfer characteristics, there's little or no difference in the transfer characteristics with respect to the type of metal that's used. And this points to the fact that the Fermi level is pinned due to defects at a given energy level below the conduction band. In the case of MOS2, and we primarily get these N-type characteristics. This is very nice work done by Jim Hohn's group a few years back, where they did mechanical transfer of graphene on 3-layer MOS2 and got wonderful results. As I mentioned earlier, one can use HBN as a buffer layer between the 2D semiconductor and the metal to prevent damage and reactions of the metal between the 2D semiconductor, and the HBN is being sufficiently thin that it can facilitate tunneling from the metal into the 2D semiconductor. There was a recent work done by Duan's group where they showed that if you simply mechanically transfer gold onto MOS2, one can make very good contacts. There's been very old work done that showed that indium, which is a very soft metal, can make very good contacts to very gentle and good contacts to molecules. So we took the approach of, so we go back to the previous slide, we took this approach because one of the things that became very clear when we tried to deposit different types of metals onto our 2D semiconductors is that there was always a Fermi level pinning. And it was clear from the literature that there was a lot of damage when you did direct deposition of metal onto the 2D semiconductor. So we took inspiration from this work by simply hypothesizing that if you have a very soft metal like indium, and if we deposit it very gently on top of a single layer MOS2 that's grown by CVD, that we should be able to create a very soft, a very clean interface. That is, we should be able to prevent any damage from the deposition of indium metal, because that's done at low temperature. The evaporation is done at low temperature. The thermal energy of indium is also very low, so you can sort of gently come and deposit onto the monolayer MOS2. And so these are cross-sectional TEM images of MOS2. So this is right underneath the contact. This cross-sectional TEM is taken from a device that we tested, got the IV characteristics from, and then we did cross-sectional TEM to look at the structure or the interface between the MOS2 and indium electrode. What we found is that there is this clean interface, van der Waals interface, and the reason why we call it van der Waals interface is because when one looks at the electron energy loss spectroscopy results of, we take the yields measurements by focusing the TEM probe onto the sulfur atom. We measure the yield spectrum and we get this black curve. Then we take a multi-layer sample. We go down to the 5th layer, we focus our yields probe on a sulfur, that's 5th layer down, and we measure the yields, and we find that they're very similar. The spectra are very similar. And what this indicates, yields gives you information about the electronic state of the atom. And we see that electronically, this sulfur atom that's right next to the interface and this sulfur atom that is in 5th layer down, electronically is no different. And so since the interaction between the sulfur atoms in MOS2 is van der Waals, we're also claiming that the interaction between the metal and the sulfur is also van der Waals type of interaction. So in contrast, if you just, for comparison, if you take something like titanium and deposit it directly on MOS2, we find that there is substantial difference in the EO spectra, but one can also visually see that there's quite a bit of damage as well. Let's see, how am I doing on time? Okay. And so we were quite happy to see this clean interface. We also, of course, checked the interface with XPS and other techniques as well. And we found that, so then we decided to carry out electrical measurements. And the electrical measurements showed that this is a transfer length measurement of resistance as a function of the channel length. And one can see that the contact resistance in this case of indium contacts on single layer MOS2 is around 3 kilomicron. This is still substantially larger than what one gets in silicon, or what one gets by phase engineering, but this is amongst the lowest values that have been measured so far. And this translates into very nice FET characteristics with mobility values at room temperature that are in excess of 100 centimeters squared per volt second, with reasonably high saturation current density. You see that the output characteristics are also linear, all suggesting that the contact properties are actually quite good. And if we do a comparison of the different types of methodologies that have been used to reduce contact resistance, we see that for indium, things are looking reasonably good. And so this works on any 2D semiconductor. Niobium disulfide is a metallic 2D semiconductor, so one can achieve very low contact resistance values of the order of 200 ohm micron. On tungsten disulfide, we get low contact resistance as well, and that translates again into very good device characteristics with much higher current than if you had a defective titanium contact on tungsten disulfide. And so we're quite happy with the indium deposition. And now I think there are groups in Korea, in the US, and in A-Star who are actually depositing indium capped with gold or some other metal as a very high quality contact. Measurements have also shown that these contacts are actually quite stable all the way down to low temperatures of sub 4 Kelvin as well. So we felt very comfortable over the last year and a half that we're able to make good N-type contacts using indium as the electrode. But to move towards this tunnel FET idea that I alluded to earlier, we also require P-type contacts. And so we've been working on tuning the work function of the electrodes, indium alloy specifically, by alloying it with high work function metals. So one thing that I didn't mention in the earlier slides is that the way we make indium electrodes is that we deposit indium first. The typical thickness of indium is of the order of 3 nanometers, and then we typically cap it with gold. And in our TEM analysis, what we found is that after annealing at 200 degrees C, where we get the best device characteristics, we find that the indium and gold have completely intermixed, but the interface is still preserved. The van der Waals interface is still preserved. And so this intermixing gave us the idea that what if we what if we deposit the indium first and then say high work function metal like palladium on top, and then cause intermixing with the work function increase. So we've carried out some Kelvin force measurements, Kelvin probe force measurements for work function extraction. And what we found is that pure gold has, of course, a work function of 5. When we when we mix the indium, because it's the indium that's primarily interacting with the 2D semiconductor, the work function decreases down to around 4.05. But if we alloy the indium with palladium, we're able to increase the work function to around 4.23. And we wanted to see if this higher work function translated into different device characteristics. So here we made devices on tungsten diselenide, and here we show indium gold as the electrode, but we get similar sort of characteristics, interface characteristics with indium palladium as well. And so if we look at the transfer characteristics, if we have this tungsten diselenide and we deposit indium gold as the electrodes, we get this black transfer characteristics where one can see that the electron current part of the transfer characteristics dominates with much higher current. But if we then make electrodes with indium palladium, we're able to see that we can increase the whole current quite dramatically with respect to indium gold. So this suggests that there is some influence of work function engineering in terms of injection of holes with a higher work function metal relative to say indium gold. And then we get nice output characteristics on both the p-type and the n-type. So we're able to at least make ambipolar types of devices with indium alloyed contacts. So we've been sort of studying how the alloying affects the device characteristics, and so this is some cross-sectional TM image with EDX mapping, and one can see that before annealing, there is a concentration of indium. It's kind of hard to see, but there's a concentration of indium at the interface between the metal and the semiconductor. This is the gold map. After annealing, we can see that there's a uniform distribution of indium and gold throughout the contact region. And one can see that before anneal, we primarily get this n-type behavior, but after anneal, we can get some hole current as well, because you have some diffusion of gold to the interface. Now, this annealing is really tuning the interface here and refining the interface, because if we plot the mobility as a function of temperature, annealing temperature for the indium gold contacts, we see that there is some increase up to 200 degrees C, after which we start to get a decrease in mobility. And when one compares to pure gold contacts, what one finds is that there is a decrease in mobility almost right away with annealing temperature. And this is, we feel that the gold starts to react with the 2D semiconductor and disrupts the interface right away. And in the case of indium, the indium provides buffer for that preventing that reaction from happening. So we've also, in order to try to make good p-type characteristics, we've also looked at alloying the indium with platinum, and if so these are again cross-sectional TEM sample analysis of pure platinum on multi-layered MOS2 in this case, or sorry, tungsten disulfide, multi-layered tungsten disulfide. And what we find is that direct deposition of high work function metals like platinum causes damage at the interface. But if we buffer the platinum with a thin layer of indium, we're able to maintain this clean interface. And the consequence of that, the electrical consequence of that, is that we can get this p-type characteristic with pure platinum with a relatively low current. But if we are able to preserve the interface, then we're able to enhance the current by a couple of orders of magnitude. So the placement of indium as a buffer layer for high work function metal really prevents damage at the interface and boosts the p-type characteristics of tungsten in this case. Okay, so in the last few minutes, let me just talk about, so the other sort of main focus in my group, besides contacts and devices, is catalysis. So I just want to sort of try to connect how contact resistance is also important in electrocatalysis. So we've been looking at the hydrogen evolution reaction, the oxygen evolution reaction. And so in the case of hydrogen evolution reaction from electrocatalysis, there is the first step in the reaction is this charge injection from the counter electrode to the catalyst. And this charge injection, in electrochemistry is often referred to as charge transfer resistance and other things. And this really sort of influences the reaction kinetics of the electrocatalysis. But we view this as contact resistance, and over the years we've worked on how can we reduce this contact resistance using the things that we learned for our FETs work to boost the electrocatalytic performance of these materials. And so we've pioneered these micro-electrochemical cells for electrocatalysis, which allows us to measure the electrocatalytic properties of individual sheets of MOS2 or tungsten disulfide, any transition metal dichalcogenide. And it simply involves patterning electrodes similar to what we do for FETs on as-grown CVD samples. And then what we can do is we can open up windows on top of these TMDs and use electrolyte to do electrochemistry very locally on an individual flake using the reference electrode, counter electrode, and the working electrode. And this gives us a lot of information about the number of atoms that are active in the catalysis reaction and so forth. But one study that we conducted a few years ago was to look at really the influence of contact resistance on electrocatalysis. So of course it's not surprising for us that if the contact resistance is high, as shown here, the catalytic activity is poor. So here, this is plotting the current density as a function of the applied potential for a reaction to occur. And the higher the current density, the better the reaction is proceeding. And one can see that for a low contact resistance, the reaction and the current density is much better. And so this charge injection and improving the contact resistance between the catalyst and the support is a very important parameter that was neglected, in our opinion, by the electrocatalysis community for a long time. So we've utilized that knowledge to design new types of supports for improving the catalytic performance. So this is results for the oxygen evolution reaction. So for splitting water to obtain hydrogen, one has to have the hydrogen evolution reaction and the oxygen evolution reaction. So both reactions have to occur simultaneously. So we've been looking at OER as well. And a few years ago, we showed that if one reduces graphene oxide by irradiating with microwaves, we can make this very high quality graphene-like carbon. And then if we put the catalyst on this very high quality graphene-like carbon that's GO reduced by microwaves, we're able to improve the performance of the catalyst with respect to if the catalyst was placed directly on glassy carbon or just on RGO. So what this shows is current density is a function of overpotential. And we can see that the reaction starts to proceed, which is indicated by this red curve, at a much lower overpotential when the catalyst, in this case nickel iron layered double hydroxides, when we put these catalysts on microwave RGO, we can see that the overpotential of the reaction is decreased quite dramatically relative to other forms of carbon. And this is because this microwave reduced graphene oxide is more conducting and leads to more intimate contact between the catalyst and the support. But not only that, having the right sort of support also allows us to increase the lifetime and stability of the catalyst for this reaction. So this contact is not only important in transistors, it's also very important in electrocatalysis. And very recently, we published a paper last year where we showed that we can actually take these metallic TMDs like niobium disulfide, and we can build an electrolyzer for splitting water, and we can achieve current densities that are of the order of 1 amp per centimeter squared. So this is real sort of electrolyzer current density. So I'm not going to talk too much about electrocatalysis, but I just wanted to give a flavor for how the contacts work is related to lots of other things as well. So with that, let me conclude and perhaps take a few questions. So I'd like to thank Yan Wang, who did all the work on the devices, field effect devices, and Huyong Zhang and Zhong Chan from UNIST, who did the cross-sectional TEM. And some of the catalysis work was done by June and Dr. David Forey, who's now in CNRS Montpellier. So with that, thank you, and I'm happy to take any questions.
Manish, thank you so much for this wonderful talk on the importance of being soft with 2D materials. This is great. So folks, you can ask the questions now, write your questions there, and then Manish will select the questions, okay?
Yep.
And we'll go from there.
So there was a question, is there any 2D layered material with mostly ionic conductivity rather than electronic? What kind of functionalities such material can add to the 2D community? Yeah, I mean, that's a good question. So ionic conductors are, of course, very important. The kinds of 2D materials that I was talking about do not exhibit any ionic conductivity. But of course, in the battery field, there are several different types of layered materials, mostly oxides. So for example, niobium tungstenate exhibits very good lithium ion conductivity. In fact, it becomes superconducting when you put enough lithium in. So it'd be, but if we can have ionic conductivity in some of these 2D materials, that could also be very useful for electrochemistry applications. Okay, then there was another question that says, is there any reaction between indium and TMDCs during annealing? Thank you. So we do not, this is a little bit of surprising to us. When we do the annealing, the indium and the gold sort of interdiffuse, form an alloy, but we do not see any reaction at the interface. That is, the interface remains van der Waals type of interface, which is a good thing, but we don't quite understand exactly why. Another question is, how do you compare your choice of indium as a contact versus using 2D materials as contact like graphene? Yeah, so I think putting graphene or HBN as a tunnel barrier are all sort of similar sort of strategies. I think the graphene also works as a good contact, but the important thing is that if you have a metal contacting, you have a much higher density of states. And of course, it makes the device fabrication process much easier. If we think about scaling up and other things, if ideally, if you can evaporate contact using E-beam evaporation or sputtering or some similar thin film deposition technique, then integration is a little bit easier. I would like to ask, will you expect, if buffer layer thickness of indium change, are there any? Yeah, I mean, by changing the indium thickness, we just stuck to very thin indium because we wanted the interface to be clean. I think there has been work done on increasing the thickness of indium, and the interface remains van der Waals. It does not. There's no dramatic change in the device characteristics. So a question from Jorge says, after exfoliation, how long is the 2D exposed to ambient condition? So that's a very good question, Jorge. It's things that people don't talk about very much. We do CVD growth, so we've not, although we do mechanical exfoliation as well. I think it's important not to keep your samples exposed to the atmosphere for too long, because if you have adsorbed layers on top of your 2D layer, if you deposit metal on top, the adsorbed layers could be trapped between the metal and the 2D semiconductor, and that could create interface states as well. So you want to try to keep it in a dry environment, preferably a glove box, to prevent any adsorption of reactants on the surface. Yeah, so did you perform any surface cleaning before doing the work function measurements? I think, again, we try to be very careful at ensuring that the surface are as clean as possible. We didn't take any special precaution except to be sort of very careful not to expose the samples to the ambient for too long. Okay, so there's a question: why does the work function engineering work so well in the case of indium alloys? Why isn't the formula of pinning such a problem here? So the idea here is that we'd like to keep the interface as clean as possible, but change the work function of the metal. So the indium allows us to change the work function by alloying it with high work function metals, but the interface, does not seem to be impacted, and that's what I think gives us the good characteristics. What else? So how much indium do you deposit? All the alloys that you tried result in van der Waals contact length. Yeah, so as I said, we try to minimize the amount of indium. I said 3 nanometers. I think 3 to 10 nanometers is quite normal. What was I lost track of the second question, because I was reading the other question. Yeah, so 3 to 10 nanometers is quite standard. Although I have seen papers now on arXiv that have grown thicker indium layers. So why there's no damage at all caused by kinetic energy transfer for indium contact on MOS2 during E-beam evaporation? We know the damage happens in EU contacts on MOS2. Is it because the melting point is much lower? Yes, exactly. That's exactly right. Indium is very soft, so the amount of power that we need to evaporate, that we need to apply to the crucible, is very low, which allows for very gentle deposition without damage. Okay, what is the importance of having defects in the basal plane and still minimize contact resistance for electrocatalysis? So defects, especially in the form of sulfur vacancies, are important for electrocatalysis because they're the active site. So when you remove sulfur, you expose the molybdenum, and it's the molybdenum that is the active site in electrocatalysis. The contact resistance, has to be minimized using, these van der Waals contacts or phase engineered contacts. So the two are not necessarily related. Okay, there's so many questions.
It's growing as you
growing.
speak. It's growing.
So, as you mentioned, that the operating electronic devices in our world contribute to 3% of global CO2. Have you estimated how much your work could reduce this? Of course, that's these the transistors are just one part of the equation. I think that it's going to be very difficult it's very difficult to estimate what one specific contribution will make towards reduction of a CO2 emission in a large industry like electronics. But the basic idea here is that if you reduce the operating voltage and can still maintain the large signal to noise ratio, then you can at least decrease the power. That should have some positive effect. Although it's very hard to calculate specifics. Let's see. Right. Okay, so what are the highest electron and hole mobilities obtained in these structures? So the highest that mobility we obtained was of the order of 160, 170 centimeters squared per volt second. Typically, with indium contacts, we achieve mobility values that are 100 or above on CVD samples, which for us is really really good and indicates the high quality of the contacts. There's a very good question here about how about metallic contacts? Could indium also solve the contact resistance problem? So I think this is something that I'm constantly telling my students and my group members to do. You could easily take indium and alloy it with cobalt or nickel, and you have you can have a ferromagnetic contact with that's with a van der Waals interface, and it can be quite useful for spin injection and other things. So I think there's enough groups now starting to work on indium-based contacts around the world that it's a matter of time before somebody demonstrates that. I think there's a lot of potential for making magnetic contacts using indium alloying method. So if the indium is annealed in some selenium environment, could it form indium selenide or any alloy formed 2D material? Yeah, so we've not. I mean, in principle, that's how these TMDs are made, but we've not seen any evidence of indium selenide. We looked very closely using XPS and other techniques, but at least within the annealing conditions that we make, we've not seen any alloying of indium with selenium. Yeah, so will there not be a possibility of oxide formation when a thin layer of indium is deposited? So that's the main reason why we cap it with gold. Indium is very soft, and so making pure indium contacts is challenging, and so we, just to be safe, we simply cap it with gold or some high work function metal to protect it. Right. So is soldering indium contact onto 2D layers same as evaporated? I guess it could be, but although it's very difficult to solder anything to something that is only 3 atoms thick. So, right. Do you see any, Antonio, that I need to address?
Oh, I think you did a wonderful job. I want to thank you once again for the amazing talk. I'm sure it inspired a lot of people today to work into this beautiful problem, and definitely extremely relevant for 2D technology. And once again, Manish, thank you so much for being here today. And folks, thank you so much for being in our seminar today. And very soon, we're going to put an advertisement for the next seminar. But I want you guys to have a good time. Be safe, be healthy. Manish, thank you so much. Hope to see you in person soon after this lockdown somewhere around the world. Okay.
Thanks very much, Antonio. Thanks, everybody. Take care.
Thank you,
Bye-bye.
guys. Bye, guys. Bye, everybody.